if you have a ketone, either lithium aluminum hydride, sodium borohydride, it doesn't really matter. Both of them will make an alcohol. Aldehyde, same thing. If it's more even reactive than ketones, sodium borohydride, lithium aluminum hydride, they both make the same alcohol. But when it becomes a carboxylic acid, that's the one things become different. Lithium aluminum hydride, it becomes a primary alcohol. Sodium borohydride with the carboxylic acid, no reaction because it's not reactive. And then ester, again, the carbonyl is also the ester functional groups, but they react differently than the ketones and aldehyde because of the presence of the living groups. It's the same reason why the ester and acid chloride react differently with the grignard, as we discussed in the last class. Same thing we can expect with the hydride too. If the lithium aluminum hydride is used with an ester, it's going to make an aldehyde as intermediate, but that's going to react further to becomes a primary alcohol. I'll show you the mechanism here. Sodium borohydride with an ester, nothing is going to happen. So clearly, you really have to choose the right reagent for the occasions. All right, so this is time to solve the mystery. Why the carboxylic acid gives a primary alcohol? Why the ester gives a primary alcohol? I mean, this is kind of the things that we have put it down, but I don't want you to memorize it. I want you to drive it. So I'm going to show you how this thing happens. Start with the ester. The ester and ketones and aldehyde, the difference is we have a living groups, right? That's the what makes differences. Hydride is the one that makes an attention of carbonyl because the carbonyl still has electron deficiency, and electron deficient carbon of the carbonyl get attacked by the nucleophilic hydrogen. That's basically the same way the grignard will react with ester first. That makes an attack, high electrons go to the oxygens. We get the alkoxide as intermediate as we expect. But this alkoxide doesn't stay like this because it has a living groups. That's the differences. That's the only differences, but that's the why it behaves differently. It will make a carbonyl back because a carbonyl is a very stable, thermodynamically stable function. So it will make a carbonyl back by kicking this methoxide off. So you get the aldehyde. But we're never going to see the aldehyde as a product because the lithium aluminum hydride is a really, really powerful reductant. When there's a high aldehyde there, like this, it'll just reduce one more time. So it has a 4 hydrogen there. Lithium aluminum hydride has a 4 hydrogen to use. So you have a lot of a hydride there. First hydride is consumed to make an ester to the aldehyde. But second hydride makes an attack to the aldehyde. It becomes an alkoxide by delivering 2 hydrogens. But after that, there's no living group. It's going to be stuck like this until the end. When you add the water, it will get protonated, then you get the primary alcohol. So that's the reason why the ester makes a primary alcohol, because the 2 hydride is delivered. First hydride delivery makes an aldehyde, but it will react one more time to become a primary alcohol. Eventually, 2 hydrogens are delivered, right? But what about the carboxylic acid then? How that works? It works a little different way, but eventually it makes the same thing. Carboxylic acid with the lithium aluminum hydride. What is going to be the first thing to happen? So far, you've seen that this nucleophilic hydrogen hydride, that's the one that making attack to carbonyl and pushing it up. Right? That's what we see every molecule with a carbonyl. But something that you shouldn't forget is what is going to be the fastest reaction is the acid-base reaction. What is an acid? Carboxylic acid, as the name suggests. You got proton there. Proton with an H minus, which is basic hydride. So what's going to happen when we mix them together is not this attacking the carbonyl. This hydride will get the high proton. You are basically bubbling the hydrogen gas out. So first hydrogen is consumed. You see the bubble comes out because you are producing the hydrogen gas. obviously that's going to be the situation that I just told you. It could be dangerous. So that's why you want to lower the temperatures. You don't want to provide the heat, and then you don't want to provide oxygens, and you probably want to exchange the head gas with something else. So anyway, so this first reaction is not the hydrogen hydride attacking the carbonyl. It's actually the hydride get a proton. It's acid-base reactions. So you've got the hydrogen gas bubbled out, but what you got in the end is just aluminum basically make the bond with an oxygen. And that kind of looks like an ester, right? It's an ester. It's aluminum ester. But now, by doing the acid-base reactions, you are basically making carboxylic acid as aluminum ester. What it does, the second hydride is going to be make an attack. You get the alkoxide. This comes back, make a carbonyl, and kicking these things out. So you are getting the aldehyde. And the aldehyde, obviously, going to go one more reaction. So you get the primary alcohol as the ester did. So basically, carboxylic acid is going to consume 3 hydride. First one, it will make a carboxylate and make an ester with aluminum. Second hydride is used to convert the aluminum ester to the aldehyde. And the third hydride is finally reducing the aldehyde to primary alcohol. So that's the reason carboxylic acid, ester, all of these things all reduce down to the alcohol, primary alcohol, because it's going to be consuming multiple hydride. Anyway, so this is a reason why you see that, but this happens only with the lithium hydride. Sodium borohydride doesn't do these things at all. So how that can be put into the question, let's talk about these examples here. Let's say this molecule is reacting with sodium borohydride or lithium aluminum hydride. Then what will occur? So let's talk about the lithium aluminum hydride first. The lithium aluminum hydride, see there's a carbonyl of the aldehyde, there's a carbonyl of the ester. And then the lithium aluminum hydride doesn't care where the carbonyl is. It's basically just going to go react both. So hydride attacking this aldehyde, that's going to make these are carboxyl groups here, and then this is basically that's it. Nothing else will happen. But when this hydride attacking the carbonyl of the ester, you get that intermediate first, but you know that that has a leaving groups right here. So because of that, once that happens, you get the carbonyl back by kicking this methoxide going away. That will make an aldehyde. That will get reduced one more time. So eventually, you get everything becomes an alkoxide, but that will get protonated in the end. So you get both of them becomes an alcohol. So that is what happens when you have a powerful reagents like the lithium aluminum hydride. They just react in the both. But okay, the ester side of the acid, carboxylic acid or acid chloride, whatever, you just have to be careful because they're not delivering just one hydride, they're delivering multiples until there's nothing else can happen. Compared to these steps, if you're using sodium borohydride is much more selective. It can only react with the ketones or the aldehyde, nothing else. So there's a carbonyl of the ester, but the sodium borohydride is not going to touch it at all because it doesn't have no power. Only thing it can do, aldehyde, that side only getting reduced, ester survives. So that's the difference is if you really don't want to pay attention. And because we always ask the questions about it. The right reagent for the right circumstances. I'm pretty sure that that's kind of the things that you should pay attention for the other reagents as well, in case there's any reactivity difference. All right, so a few more things until the end of the chapter 10. The catalytic hydrogenation, that's something that hydrogen gas is used with the metal catalyst. It's something that we discussed with using double bonds and triple bonds, carbon-carbon double bonds, carbon-carbon triple bonds. But actually the catalytic hydrogenation can be also used to reduce carbon oxygen double bonds too. Platinum does this, and nickel does that too. So if you treat the ready nickel with a hydrogen gas, this molecule, what happens to double bonds is reduced. You're adding a hydrogen to double bonds. Carbonyl also reduced because you're adding a hydrogen gas to the carbon, oxygen double bonds. So you get alcohol here, you get the double bonds reduced. So in case you have to reduce the double bonds, you have to reduce the carbonyl. You can do two things in one step by just treating with the hydrogen gas with a ready nickel. But there are situations that you may want to reduce just one, not both. In case you want to reduce these double bonds, what would you prefer to use? Double bond reductions can be done only with a few things, the hydrogen gas, but nickel does this, and platinum has a potential to do that too. The only thing that remains is a palladium. The palladium somehow it has a higher reactivity with the double bonds compared to the carbonyl. So if you want to just reduce the carbon-carbon double bonds without touching this carbonyl, then the palladium would be a good choice. If you want to reduce both of them, sure, the nickel definitely is something you can do. But what if you only want to reduce this carbonyl, not touching that? Then what would you use? Oh, the C is just a carbon support. It's like it's charcoal, carbon black, just material that you just deposit them out into it. We're not using palladium as a chunk because that would be really expensive. The small drops of the palladium are coated on the material like the carbon black or the charcoal. So that's why C is a purpose. So if you want to reduce only the carbonyl, don't want to do anything with double bonds, what would you choose? Which reagent? Then is what we just talked about, the hydride. Lithium aluminum hydride, sodium borohydride. They do react with the carbonyl because of these things are polar double bonds. We got the electron deficient carbon. These carbon-carbon double bonds, there's no electron deficiency, so lithium aluminum hydride, sodium borohydride doesn't do anything about it.